Hello and welcome to Domain 4 of the CISSP certification course offered by Simplilearn. This domain provides an introduction to the communications and network security. Let us explore the objectives of this domain in the next screen. After completing this domain, you will be able to describe the various secure network architectures and designs, recognize the importance of securing network components, list the different secure communication channels, list the common network attacks and the countermeasures. Let us begin with a scenario highlighting the importance of communication and network security in the next screen. Kevin, who is preparing for his CISSP exam, read an internal case file on a recent spam attack on Nutri Worldwide Inc. At the Minnesota plant, a vendor who had visited the plant used his laptop to complete a few transactions. He connected to the wireless after taking approvals. He used his flash drive to take backup of the transactions. The flash drive had viruses, and these entered the network through his laptop, causing the local server to crash. This had far-reaching effects. In the next screen, we will focus on the introduction to secure network architecture and design. Various communication protocols define communication. The protocols can be grouped into stacks, family, or suite. There are two most popular models, OSI and TCP/IP models. Both the models divide communication into different layers. Each layer addresses specific requirements of the communication process. Security can be addressed more efficiently using the layered approach. Let's now discuss the OSI reference model. International Organization for Standardization, ISO, created the Open Systems Interconnection, OSI, reference model in the early 1980s. The purpose was to help vendors create interoperable network devices. OSI is a standard model for network communications, which allows dissimilar networks to communicate. The OSI reference model describes how data and network information are communicated from one computer to another computer through a network media. The OSI reference model breaks this approach into 7 distinct layers, also called the protocol stack. Layering divides a piece of data into functional groups that permit an easy understanding of each piece of data. Mapping each protocol to the model is useful for comparing protocols. Each layer has a unique set of properties and directly interacts with its adjacent layers. In the process of data encapsulation, data from one layer is wrapped around a data packet from an adjoining layer. Each layer on one workstation communicates with its respective layer on another workstation using protocols that are agreed upon communication formats. The following chart describes the OSI reference model. Please do not take salesperson advice can be used as the mnemonic phrase to remember each layer of the OSI model. Physical layer. At this layer, bits from the data link layer are converted into electrical signals and transmitted on a physical circuit. Data link layer. This layer prepares the packet it receives from the network layer to be transmitted as frames on the network. Network layer. This layer provides switching and routing technologies, creating logical paths known as virtual circuits for transmitting data from node to node. The functions of this layer are routing and forwarding, addressing, internet working, error handling, congestion controlling, and packet sequencing. Transport layer. This layer provides transparent transfer of data between end systems or hosts and is responsible for end-to-end error recovery and flow control. It ensures complete data transfer. Session layer. This layer establishes, manages, and terminates connections between applications. The session layer sets up, coordinates, and terminates conversations, exchanges, and dialogues between the applications at each end. It deals with session and connection coordination. Presentation layer. This layer provides independence from difference in data representation, as is encryption, by translating from application to network format and vice versa. The presentation layer works to transform data into the form that the application layer can accept. This layer formats and encrypts data to be sent across a network, providing freedom from compatibility problems. It is also called the syntax layer. Application layer. This layer supports application and end-user processes. Communication partners are identified, quality of service is identified, User authentication and privacy are considered, and any constraints on data syntax are identified. Everything at this layer is application-specific. This layer provides application services for file transfers, email, and other network software services. Telnet and FTP are applications that exist entirely in the application level. Tiered application architectures are a part of this layer. Let us now understand the working of the OSI model. Data is sent from a source to a destination computer. In a layered architecture model, the data passes down through each layer from the highest, application layer, layer 7 in the OSI model, to the lowest layer, physical layer, layer 1 of the OSI model of the source. It is then transmitted across the medium, cable, and is received by the destination computer, where it passes to the layers in the opposite direction from the lowest, layer 1, to the highest, layer 7. Each protocol operates at specific layers. Each protocol in the source computer has a job allocated. They are responsible for attaching its own unique information to the data packet when it comes to its layer. When the data packet reaches the destination computer, it moves up the model. Each protocol detaches and examines only the data that was attached by its protocol counterpart at the source computer. Then it sends the rest of the packet up the protocol stack to the next highest layer. Each layer at the individual destination sees and deals only with the data that was packaged by its counterpart on the sending side. Let us now learn about each layer of the OSI model in detail. The first layer is the physical layer. This layer defines the physical connection between a computer and a network and converts the bits into voltages or light impulses for transmission. It also defines the electrical and mechanical aspects of the device's interface to a physical transmission medium such as twisted pair, coaxial, or fiber optic. Communications hardware and software drivers, as well as electrical specifications, are found in this layer. The physical layer has only two responsibilities. Firstly, it sends bits and receives bits. Signal regeneration and repeating is primarily a physical layer function. Secondly, it defines standard interfaces such as RS-232 and RS-449, X.21, and high-speed serial interface HSSI. Examples of physical layer are EIA-232 or RS-232 and synchronous optical network SONET. The physical layer provides services to the data link layer. The second layer is the data link layer. This layer defines the protocol that computers must follow in order to access the network for transmitting and receiving messages. Token ring and Ethernet operate within this layer. This layer establishes the communications link between individual devices over a physical link or channel. It also ensures that messages are delivered to the proper device and translates the messages from layers above into bits for the physical layer to transmit. It also formats the message into data frames and adds a customized header that contains the hardware destination and source address. The data link layer contains the logical link control sublayer and the media access control MAC sublayer. MAC controls the way a system on the network gains access to the data and permission to transmit it. LLC controls frame synchronization, error check, and flow. Bridging is a data link layer function. Examples of data link layer protocols are Address Resolution Protocol, ARP, Serial Line Internet Protocol, SLIP, Point-to-Point Protocol, PPP, etc. The data link layer uses services provided by the physical layer and provides services to the network. Third layer is the network layer. This layer defines how the small packets of data are routed and relayed between end systems on the same network or on interconnected networks. At this layer, message routing, error detection, and control of node data traffic are managed. The network layer's primary function is to send packets from the source network to the destination network. Therefore, the network layer is primarily responsible for routing. Examples of network layer protocols are Internet Protocol, IP, Open Shortest Path First, OSPF, Internet Control Message Protocol, ICMP, and Routing Information Protocol, RIP. The network layer uses services provided by the data link layer and provides services to the transport layer. The fourth layer is the transport layer. This layer defines how to address the physical locations and devices on the network, how to make connections between nodes, and how to handle the networking of messages. It is responsible for maintaining the end-to-end integrity and control of the session. Services located in the transport layer both segment and reassemble the data from upper layer applications and unite it with the same data stream, which provides end-to-end data transport services. It establishes a logical connection between the sending host and destination host on a network. The transport layer is also responsible for providing mechanisms for multiplexing upper layer applications, session establishment, and the teardown of virtual circuits. Examples of transport layer protocols are Transmission Control Protocol, TCP, and User Datagram Protocol, UDP. The transport layer uses services provided by the network layer and provides services to the session layer is the session layer. This layer makes the initial contact with other computers and sets up the lines of communication. It formats the data for transfer between end nodes, provides session restart and recovery, and performs the general maintenance of the session from end to end. The session layer offers 3 different modes: simplex, half duplex, and full duplex. It also splits up a communication session into 3 different phases, such as connection establishment, data transfer, and connection release. Some examples of session layer protocols are Network File System, NFS, Structured Query Language, SQL, and Remote Procedure Call, RPC. The session layer uses services provided by the transport layer and provides services to the presentation layer. Is the presentation layer. This layer presents data to the application layer. It functions as a translator, such as Extended Binary Coded Decimal Interchange Code, EBCDIC, or American Standard Code for Information Exchange, ASCII. Tasks such as data compression, decompression, encryption, and decryption are all associated with this layer. This layer defines how the applications can enter a network. While surfing the web, it is most likely to encounter some of the following presentation layer standards, such as Hypertext Transfer Protocol, HTTP, Tagged Image File Format, TIFF, a standard graphics format, Joint Photographic Experts Group, JPEG. Also, a standard for graphics defined by the Joint Photographic Experts Group, Musical Instrument Digital Interface, MIDI, a format used for digitized music, and Motion Picture Experts Group, MPEG. The Motion Picture Experts Group is standard for the compression and coding of motion video. The presentation layer uses services provided by the session layer and provides services to the application layer is the application layer. This layer supports the components that deal with the communication aspects of an application. The application layer is responsible for identifying and establishing the availability of the intended communication partner. It is also responsible for determining whether sufficient resources exist for the intended communication. This layer is the highest level and is the interface to the user. Some of the examples of application layer applications are World Wide Web, WWW, File Transfer Protocol, FTP, Trivial File Transfer Protocol, TFTP, Line Printer Daemon, LPD, and Simple Mail Transfer Protocol, SMTP. Let us discuss the Transmission Control Protocol, Internet Protocol, TCP/IP, in this screen. Transmission Control Protocol, Internet Protocol, TCP/IP, is the common name for the suite of protocols originally developed by the Department of Defense, DoD, in the 1970s to support the construction of the Internet. The Internet is based on TCP/IP, which is named after the 2 best-known protocols in the suite. A CISSP candidate should be familiar with the major properties of TCP/IP and should know which protocols operate at which layers of the TCP/IP protocol suite. The TCP/IP model consists of 4 layers. The network access layer, which controls the hardware devices and media that make up the network, the internet layer that determines the best path through the network, the transport layer, which supports communication between diverse devices across diverse networks, the application layer, which represents data to the user plus encoding and dialogue control. The next screen will focus on TCP/IP model layers. 4 types of TCP/IP layers are network access layer, internet layer, host-to-host layer, and application layer. At the end of the TCP/IP model, the network access layer monitors the data exchange between the host and the network. This layer is equivalent to the data link and physical layers of the OSI model. It oversees hardware addressing and defines protocols for the physical transmission of data. Example, Wi-Fi, Ethernet, token ring, ATM, and PPP. The Internet layer corresponds to the OSI network layer. It designates the protocols relating to the logical transmission of packets over the network. It gives network nodes an IP address and handles the routing of packets among multiple networks. It also controls the communication flow between hosts. The primary Internet layer protocols are Internet Protocol, IP, Address Resolution Protocol, ARP, Reverse Address Resolution Protocol, RARP, and Internet Control Message Protocol, ICMP. The host-to-host layer is similar to the OSI transport layer. It defines protocols for setting up the level of transmission service. It provides for reliable end-to-end communications, ensures the error-free delivery of the data, handles packet sequencing of the data, and maintains the integrity of the data. The primary host-to-host layer protocols are Transmission Control Protocol, TCP, and User Datagram Protocol, UDP. The application layer is exactly the TCP/IP. It is made up of everything that the application is trying to communicate using TCP/IP. TCP/IP views everything above the three bottom layers as the responsibility of the application, so that the application, presentation, and session layers of the OSI model are considered folded into this top layer. Therefore, the TCP/IP suite primarily operates in the transport and network layers of the OSI model. HTTP, FTP, and SMTP are some of the example protocols. In the next screen, we will look into the comparison of OSI and TCP/IP model. TCP/IP model is very similar to the OSI model, however, with fewer layers. The network interface layer provides physical communication and routing within a network. It corresponds to everything required to implement an Ethernet. It is sometimes described as two layers, a physical layer and a link layer. In terms of the OSI model, it covers layers 1 and 2. The Internet layer includes everything that is required to move data between networks. It corresponds to the IP protocol, but also to Internet Control Message Protocol, ICMP, and Internet Group Management Protocol, IGMP. In terms of the OSI model, it corresponds to layer 3. The host-to-host transport layer includes everything required to move data between applications. It corresponds to TCP and UDP. In terms of the OSI model, it corresponds to layer 4. The application layer covers everything specific to a session or application. In other words, everything related to the data payload. In terms of the OSI model, it corresponds to layers 5 through 7. Owing to its coarse structure, it is not well suited to describe application-level information exchange. All hosts on the Internet have a logical and numerical ID called an Internet Protocol IP address. On the Internet or any network using IP, each data packet is assigned an IP address of the sender and the recipient. Each device receives the packet and makes routing decisions based on the packet's destination IP address. IP addressing provides an unreliable datagram service. This means it does not guarantee that the packets will be delivered at all, delivered only once, or even delivered in the order in which it was sent. IP address has two parts, network and host. A subnet mask is used to distinguish between the network and host portions in an IP address. Now, let us look at the different types of IP addressing. There are two versions of the IP in use, IP version 4, IPv4, and IP version 6, IPv6. Each version explains an IP address differently. IPv4 and IPv6 are designed not to be interoperable. IPv4, or Internet Protocol version 4, is a simple form of network addressing designed to carry data across networks. It is connectionless and unreliable and provides best effort packet delivery. If it requires connections or reliability, it has to be provided by a higher level protocol carried by IP, such as the Transmission Control Protocol or TCP. Network addresses in IPv4 are 32 bits in length and are expressed as a dot decimal notation, that is, xx.xx.xx.xx, where the range of each XX is 0 to 255 decimal. A 32-bit address field allows 2 to the power 32, or nearly 4.3 billion addresses. Example of a typical IPv4 network address is 192.168.0.100. The availability of IPv4 addresses in a world where humans and their devices outnumber them became a major problem. This led to the creation of IPv6, which uses 128-bit addresses. The new address space provides the potential for a maximum of 2 to the power 128, or about 3.403 by 10 to the power 38 addresses. IPv6 became more predominant since the release of Microsoft Vista and Windows 7 operating systems. These operating systems support IPv6 and have it enabled by default. Most modern Linux operating systems, such as Ubuntu, are also by default IPv6 enabled. IPv6 addresses are represented as 8 groups of 4 hexadecimal digits separated by colons. Example of a typical IPv6 network address is FE80:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00:00::00::::::::::::::::ll B3FF:8329. The main intent of this addressing is not just to provide an adequate quantity of addresses, but to allow an effective combination of subnetwork routing prefixes at the routing node. Let us discuss classful IP addressing. Originally, the entire available IP address space was divided into 2 parts: the network number that consists of the first 8 bits of an IP address, the host address that consists of the remaining 24 bits. This resulted in only 256 possible networks in the entire Internet, which was not feasible. Thus, the concept of classful networks was introduced, which resulted in a greater number of smaller networks. There are 5 types of classful IP addressing: Class A, B, C, D, and E. Class A network consists of an 8-bit network address and a 24-bit host address. IP ranges from 0.0.0.0 to 126.255.255.255, and implied net mask is 255.0.0.0. Thus, Class A network could contain 16,777,214 nodes. 126 such networks were created for large organizations. Class B network consists of a 16-bit network address and a 16-bit host address. IP ranges from 128.0.0.0 to 191.255.255.255, and implied net mask is 255.255.0.0. Each network could contain 65,534 nodes. 16,382 of such networks were created. C network consists of a 24-bit network address and an 8-bit host address. IP ranges from 192.0.0.0 to 223.255.255.255, and implied net mask is 255.255.255.0. Thus, Class C network could contain 254 nodes. Over 2 million such networks were created. Class D network is reserved for multicast. IP ranges from 224.0.0.0 to 239.255.255.255. Class E network is reserved for research purposes. It ranges from 240.0.0.0 to 255.255.255.255. In the next screen, we will discuss the classes interdomain routing. Interdomain routing, CIDR, will be discussed in this screen. The scheme of classful networks lived for a short term. This gave rise to CIDR. CIDR is a method for allocating IP addresses and routing Internet Protocol packets. The Internet Engineering Task Force introduced CIDR in 1993 to replace the previous addressing architecture of classful network design on the Internet. The goal of CIDR was to slow the growth of routing tables on routers across the Internet and to help slow the rapid exhaustion of IPv4 addresses. IP addresses consist of 2 groups of bits in the address. The most significant bits are the network address, which identifies a whole network or subnet, and the least significant set forms the host identifier, which specifies a particular interface of a host on that network. The process of dividing a network into two or more networks is called subnetting. A subnet is a logical and visible unit of an IP network. A subnet mask determines which IP address a subnet belongs to. CIDR disposed the rigid scheme of Class A, B, and C networks and permitted the creation of subnet mask of any length, called a variable length subnet mask, or VLSM, from 8 bits to 31 bits. This permitted Internet Service Providers, ISPs, to allocate small networks to customers that did not require more than a few addresses. The introduction of CIDR led to more efficient allocation of available IP addresses on the Internet. This division is used as the basis of traffic routing between IP networks and for address allocation policies. Classful network design for IPv4 sized the network address as one or more 8-bit groups, resulting in the blocks of Class A, B, or C addresses. Classless interdomain routing allocates address space to Internet Service Providers and end users on any address bit boundary, instead of on 8-bit segments. In IPv6, however, the interface identifier has a fixed size of 64 bits by convention, and smaller subnets are never allocated to end users. CIDR notation is a syntax of specifying IP addresses and their associated routing prefix. It appends a slash character to the address and the decimal number of leading bits to the routing prefix, e.g., 192.168.1.3/23 for IPv4, and 2001:DB8::/32. Let us discuss private networks and loopback address in this screen. Not all the network addresses are available for general use. Some address blocks that are reserved include private networks and loopback addresses. Private network allows accessing a guest machine by an address not publicly accessible from the global Internet. Organizations are encouraged to assign private network IP addresses to nodes in its internal networks. It can then utilize network address translation, NAT, at its border routers to translate those private network addresses into one of its allocated addresses. The address blocks reserved for private network are 10.0.0.0 to 10.255.255.255, 172.16.0.0 to 172.31.255.255, 192.168.0.0 to 192.168.255.255. The image shows the IP packet's network address translation, where the private address is translated to public address and vice versa at boundary routers. Loopback address is a special address 127.0.0.1 to 127.0.0.255 used to signify a node's own address. As shown in the image, loopback addresses 127.0.0.1 point back to the issuing computer. Now let us look at the different types of IP addressing. The Internet layer provides different addressing types that will result in messages sent to one or more destination nodes. They are unicast, anycast, multicast, and broadcast. The unicast addressing type is the most common type of addressing, where a packet is sent to a single IP address destination. Anycast address type is where a packet is sent only to one of the groups of nodes, whichever is closest or most available. Multicast address type is where a packet is sent to a group of receiving nodes on different networks. A packet is sent to a multicast address in the range of 224.0.0.0 to 239.255.255.255. It is also sent to the routers in the network track recipients. It propagates packets to destinations as needed. Broadcast address type is where a packet is sent to a network's broadcast address, which causes the packet to be sent to all nodes on a network. Dynamic Host Configuration Protocol, DHCP, and Address Resolution Protocol, ARP, utilize broadcast nodes. Let's now discuss routed and routing protocols. Routers use router-to-router communication protocol to determine the most efficient network routes between two nodes on a network. They help routers in making good routing decisions, making the right choice about which way to forward packets. Routed protocol is a protocol which provides enough information in its network layer address to allow the packet to reach its destination. IP and IPX are the examples of routed protocol. Routing protocol is a protocol used by routers to share routing information. For example, Routing Information Protocol, RIP, is one of the earliest routing protocols. The RIP uses hop count as a primary routing metric. Fewer the number of hops for a given destination, more favored a destination will be, regardless of the actual link speeds involved. The maximum number of hops supported by RIP is 15, which seemed adequate when it was invented in the 1970s. However, this limitation is one of several reasons why RIP has given way to more scalable and reliable protocols such as OSPF and ISIS. RIP runs over the UDP protocol on port 520. Cisco's proprietary Interior Gateway Routing Protocol, IGRP, was developed to overcome the limitations of RIP. Its only routing metric was hop count. IGRP supports multiple metrics: bandwidth, delay, load, MTU, and reliability. IGRP's maximum hop count is 255. IGRP was replaced by EIGRP. IGRP does not use TCP or UDP, but runs directly over IP. It is used by routers to exchange routing data within an autonomous system. Are the types of network protocols: Transmission Control Protocol, User Datagram Protocol, Internet Protocol, Address Resolution Protocol, and Internet Control Message Protocol, ICMP. Transmission Control Protocol, TCP, provides a complete duplex and reliable connection. The incoming TCP packets are sequenced to match the original transmission sequence numbers. Any lost or damaged packets are retransmitted. TCP is costly in terms of network overhead and is slower than UDP. Reliable data transport is addressed by TCP to ensure the following goals are achieved. An acknowledgement is sent back to the sender on the reception of delivered segments. Any unacknowledged segments are retransmitted. Segments are sequenced back in their proper order on arrival at their destination. A manageable data flow is maintained in order to avoid congestion, overloading, and data loss. Port types are reserved for well-known ports 0 to 1023, registered ports 1024 to 49151, and dynamic ports 49152 to 65535. Examples include HTTP, FTP, UDP and Telnet. Is similar to TCP. However, it gives only best effort delivery, which means it offers no error correction, does not sequence the packet segments, and does not care in which order the packet segments arrive at their destination. It is referred to as an unreliable protocol. UDP does not create a virtual circuit and does not contact the destination before delivering the data. Thus, it is considered a connectionless protocol. UDP imposes less overhead, which makes it faster than TCP. This is for applications that can afford to lose a packet now and then, such as streaming video or audio. Examples include DNS, TFTP, and protocol is a network layer protocol, which handles addressing and routing. IP specifies the packet format of datagrams and the addressing scheme. There are two types of IP versions: IPv4, 32-bit addresses, and IPv6, 128-bit addresses. Protocol needs to know the hardware address of the packet's destination so it can send the packet. ARP is used to match an IP address to a media access control MAC address. ARP allows the 32-bit IP address to be matched with this hardware address. A MAC address is a 6-byte, 12-digit hexadecimal number subdivided into two parts. The first 3 bytes of first half of the MAC address is the manufacturer's identifier. This can be a good troubleshooting aid if a network device is malfunctioning, because it will isolate the brand of the failing device. The second half of the MAC address is the serial number the manufacturer has assigned to the device. ARP interrogates the network by sending out broadcasts seeking a network node that has a specific IP address and then asking it to reply with its hardware address. ARP maintains a dynamic table, known as the ARP cache, of the translations between IP addresses and MAC addresses so that it has to broadcast a request to every host only the first time it is needed. In some cases, the MAC address is known but the IP address needs to be discovered. It is sometimes the case when diskless machines are booted onto the network. Using Reverse Address Resolution Protocol, RARP, the machine sends out a packet that includes its MAC address along with the request to be informed of which IP address should be assigned to that MAC address. An RARP server responds with the Control Message Protocol, ICMP, is a management protocol and messaging service provider for IP. ICMP's primary function is to send messages between network devices regarding the health of the network. It can inform hosts about a route to a destination if there is trouble with an existing route, and it can help identify the problem with the route. Ping is an ICMP utility used to check the physical connectivity of machines on a network. HTTP works on application layer or layer 7 and is the foundation of data communication for the World Wide Web, WWW. It is a stateless protocol used to exchange or transfer hypertext. HTTP is mapped to TCP port 80. HTTP has a simple access control and authentication mechanism. It does not support encryption. The access control and authentication is carried out through an extensible set of challenge-response authentication schemes, which can be used by a server to challenge a client request and by a client to provide authentication information. Let us now discuss how HTTP proxying can be used as a security measure with HTTP. An HTTP proxy is a server that receives requests from a user's web browser and makes the request to the internet on behalf of the user. HTTP proxying hides the information of the internal network from the public network. Open proxy servers allow unrestricted access to GET commands from the internet. They can be used as stepping stones for launching attacks or to obscure the origin of illegitimate requests. An open proxy server bears an inherent risk of opening access to protected intranet pages from the internet. Anonymizing proxies provide security and allow anonymization of HTTP requests. Since HTTP transmits the data in clear text, it creates several logging information on web servers and proxy servers, which can be a security issue if an unauthorized person gets access to it. Content filtering prevents users from downloading unwanted content. It also prevents access to unauthorized services. Let us discuss the implications of multi-layer protocols in the following screen. Transmission Control Protocol, or Internet Protocol, or TCP/IP protocol suite, consists of various layers with many individual protocols and is also known as multi-layer protocol. Using multi-layer protocol, encryption can be incorporated on various layers. It gives added security. The higher layers support a wide range of protocols. The security practitioner can make use of appropriate protocol from the pool of available protocols. Use of multi-layer protocols can give rise to vulnerabilities. The security filters can be evaded by manipulating the use of protocols. There can be issues of covert channels that give unauthorized access to the system or can cause information disclosure. In the next screen, we will discuss distributed network protocol. In process automation systems, different components communicate with each other using a set of communication protocols known as DNP3 or Distributed Network Protocol. It was developed for communications between various types of data acquisition and control equipment. It is commonly used in electric and water companies. One of the examples of systems using DNP3 is supervisory control and data acquisition, or SCADA. It is a system operating with coded signals over communication channels to provide control of remote equipment. It is a centralized system that monitors and controls entire sites, or complexes of systems spread over large areas. SCADA uses many different communication methods, which include wide area networks or WANs, networking devices, and modems. It is used for communication between a master station and remote terminal units, or RTUs, or intelligent electronic devices, or IEDs. Let us discuss the LAN or network technologies in the next screen. There are three types of LAN network technologies: Ethernet, token ring, and fiber distributed data interface, FDDI. Ethernet, defined in IEEE 802.3, played a major role in the rapid spread of LANs in the 1980s. The architecture was flexible, relatively inexpensive, and it was easy to add and remove devices from the LAN. It is the most popular LAN architecture. The physical topologies that are supported by Ethernet are bus, star, and point-to-point. However, the logical topology is the bus. With the exception of full duplex Ethernet, which does not have the issues of collisions, the architecture uses CSMA-CD. This protocol allows devices to transmit data with a minimum of overhead compared to token ring, resulting in an efficient use of bandwidth. Because devices must retransmit when more than one device attempts to send data on the medium, too many retransmissions due to collisions can cause serious amount of degradation. The Ethernet standard supports coaxial cable, unshielded twisted pair, and fiber optics. Ethernet was originally rated at 10 Mbps. However, with 10 megabyte disk drives, users quickly figured out how to use and exceed its capacity. To meet the growing demand for more bandwidth, 100 base TX, 100 Mbps over twisted pair, and 100 base FX, 100 Mbps over multimode fiber optics were created. When the demand grew for even more bandwidth over unshielded twisted pair, 1000 base T was defined, and 1000 base SX and 1000 base LX were defined for fiber optics. These standards support 1000 Mbps. IBM originally designed Token Ring IEEE 802.5. Token Ring was adapted with some modification by the IEEE as IEEE 802.5. Despite the architecture's name, Token Ring uses a physical star topology. The logical topology, however, is a ring. Each device receives data from its upstream neighbor and transmits to its downstream neighbor. Token ring uses ring passing to mediate which device may transmit. A special frame, called a token, is passed on the LAN. To transmit, a device must possess the token. To transmit on the LAN, the device appends data to the token and sends it to its next downstream neighbor. Devices retransmit frames whenever the token is not the intended recipient. When the destination device receives the frame, it copies the data, marks the frame as read, and sends it to its downstream neighbor. When the packet returns to the source device, it confirms that the packet has been read. It then removes the frame from the ring. Token ring is now considered a legacy technology that is rarely seen, and only then because there has been no reason to upgrade away from it. Token ring has almost entirely been replaced with Ethernet technology. FDDI is a token passing architecture that uses two rings. Since FDDI employs fiber optics, FDDI was designed to be a 100 Mbps network backbone. Only one ring, the primary, is used. The other ring, secondary, is used as a backup. Information in the rings flows in opposite directions from each other. Hence, the rings are referred to as counter-rotating. If a break or outage occurs, the ring will then wrap back the other direction, keeping the ring intact. FDDI is not considered a legacy technology and has been supplanted by more modern transport technologies. Initially, asynchronous transfer mode, ATM, but more recently, multi-protocol label switching, MPLS. Like token ring, FDDI is a token passing media access topology. The major advantage of FDDI is that it operates over long distances with high speeds and less electromagnetic or radio frequency interference. Let us begin with transmission media. Transmission media is used for transmitting data from a source to a destination. Classes of transmission media includes conducted or guided media and wireless or unguided media. Types of transmission media include unshielded twisted pair, shielded twisted pair, coaxial cable, and fiber optic cable. In the next screen, we will discuss the types of transmission media. Pair cabling is a relatively low-speed transmission medium consisting of two insulated wires arranged in a regular spiral pattern.
The wires can be shielded, STP, or unshielded, UTP. STP cable is shielded, therefore it has better electromagnetic interference, EMI, immunity. UTP cabling is a 4-pair wire medium used in a variety of networks. It does not require the thick spacing between connections that is necessary with coaxial type connections. It is unshielded, therefore is more susceptible to EMI and crosstalk. UTP comes in several categories. The category rating is based on how tightly the copper cable is wound within the shielding. They are: Category 1, used for telephone communications and not suitable for transmitting data. Category 2, specified in the EIA-TIA 586 standard to be capable of handling data rates up to 4 million bits per second Mbps. Category 3, used in 10-base-T networks and specified to be capable of handling data rates of up to 10 Mbps. Category 4, used in token ring networks and able to transmit data at speeds of up to 16 Mbps. Category 5, consists of 4 twisted pairs in a single jacket. Maximum length is 100 meters. Suitable for 100 megabits and can be used for gigabit Ethernet. Category 6, backward compatible with Category 5 and 5E. Higher specifications for noise and crosstalk. Suitable for gigabit Ethernet. Maximum cable length is 100 meters. Category 7, more stringent than Category 6 cabling. Cat 7 is suitable for 10 gigabit networks. Maximum length is 100 meters. The outer cylindrical conductor of a coaxial cable surrounds a single inner wire conductor. It needs repeaters in every 200 to 500 meters and works at 2 to 50 Mbps. 2 types of coaxial cables are currently used in LAN. 50 ohm cable used for digital signaling, 75 ohm cable used for analog signaling and high-speed digital signaling. Coax requires fixed spacing between connections. Coax is more expensive, yet it is more resistant to electromagnetic interference, EMI, than twisted pair cabling. It can transmit at a greater bandwidth and distance. Coax can come in 2 types of LANs: thin net, RG58 size, thick net, RG8 or RG11 size. There are 2 common types of coaxial cable transmission methods. Baseband. The cable carries only a single channel. Baseband is a transmission method that is accomplished by applying a direct current to a cable. The current or signals hold binary information. Higher voltage usually represents the binary value 1, whereas lower voltage represents the binary value 0. Baseband permits only one signal to be transmitted at a time. Example, Ethernet. Broadband. The cable carries several usable channels such as data, voice, audio, and video. Broadband includes leased lines T1 and T3, ISDN, ATM, DSL, broadband wireless, and CATV. It carries several signals over different channels. Cable carries signals as light waves, allowing higher transmission speeds and greater distances due to less dilution. It is also called optical fiber. Fiber optic cable is the most reliable cable type, and it is also the expensive one to install and terminate. The light source transmits the optical signal on the fiber cable. There are 2 types of light sources: light-emitting diodes, LEDs, and diode lasers. Light-emitting diodes, LEDs, are the sophisticated LEDs found in consumer electronic, less expensive than diode lasers. They offer less bandwidth over a shorter distance. Diode lasers are an expensive alternative. They require more expensive fiber cables and light detectors, and the carriers on their backbone use this optical source. There are 2 types of optical fiber, such as multimode fiber and single-mode fiber. Multimode fiber, where the light is transmitted in different modes or paths in fibers that are about 50 to 100 microns in diameter. Single-mode fiber is about 10 microns in diameter. The transmitted light takes a direct path down the center of the fiber. Fiber optic cable has 3 basic physical elements, such as core, cladding, and jacket. Core is the innermost transmission medium, which can be glass or plastic. Cladding is the next outer layer, also made of glass or plastic but having different properties. It helps reflect the light back to the core. Jacket is the outermost layer, providing protection from heat, moisture, and other environmental elements. Let's now discuss the different types of network topologies. A network topology defines the manner in which the network devices are organized to facilitate communications. A LAN topology defines this transmission manner for a local area network. There are 5 common LAN topologies, such as bus, ring, star, hierarchical, and mesh. In a bus topology, all transmissions of the network nodes travel the full length of the cable and are received by all other stations. Ethernet primarily uses this topology. However, when any station on the bus experiences cabling termination errors, the entire bus can cease to function. In a ring topology, the network nodes are connected by unidirectional transmission links to form a closed loop. Token ring and FDDI use this topology. In a star topology, the nodes of a network are connected directly to a central LAN device. The logical bus and ring topologies are often implemented physically in a star topology. Although Ethernet is logically thought of as a bus topology, its first implementations were ThinNet and ThickNet on a bus. 10BASE-T is actually wired as a star topology. It provides more resiliencies for the entire topology when a station experiences errors. Hierarchical or tree topology is a bus-type topology where branches with multiple nodes are possible. In a mesh topology, all the nodes are connected to every other node in a network. This topology may be used to create backbone redundant networks. A full mesh topology has every node connected to every other node. A partial mesh topology may be used to connect multiple full mesh networks together. Let us discuss network transmission channel in the following screen. No matter what type of media access technology is being used, the main resource that has to be shared by all systems and devices on the network is the network transmission channel. The media access technologies are Ethernet over STP/UTP in the corporate network, token ring over coaxial cabling for LAN, FDDI over fiber for backbone connectivity, or Wi-Fi over a frequency spectrum. There must be methods in place to make sure that each system gets access to the channel, that the system's data is not corrupted during transmission, and that there is a way to control traffic in peak times. Examples of media sharing technologies include CSMA-CD, CSMA-CA, token passing,
under the Ethernet Carrier Sense Multiple Access, or CSMA with collision detection, or CD media access process, any computer on a CSMA with CD LAN can access the network anytime. Before sending the data, the CSMA with CD hosts listen to the traffic on the network. A host that wants to send the data waits until there is no traffic. Ethernet enables any host on a network to transmit whenever the network is quiet. In addition, the transmitting host constantly monitors the wire to ensure no other hosts begin transmitting. If the host detects another signal on the wire, it sends an extended jam signal, which causes all the nodes on the segment to stop sending data. These nodes respond to the jam signal by waiting before attempting to transmit again. CSMA with CD was created to overcome the problem of collisions that occur when packets are simultaneously transmitted from different nodes. Collisions occur when two hosts listen for traffic and, upon hearing none, they both transmit simultaneously. In this situation, both transmissions are damaged and the hosts must retransmit at a later time. Let us discuss the Carrier Sense Multiple Access with Collision Avoidance in the next screen. In Carrier Sense Multiple Access with Collision Avoidance, or CSMA, workstations are attached to two coaxial cables. Each coax cable carries data signals in one direction. A workstation monitors its receive cable to determine whether the carrier is busy. Then it communicates on its transmit cable if no carrier is detected. It sends a short message, ready to send, or RTS, to avoid any collision. RTS communicates to everyone to retreat for that duration. It also contains destination address and duration of message. Once the medium is free, destination sends a message, clear to send, or CTS. Thus, The workstation transmits its intention to send when it feels the line is clear due to a precedence that is based on previously established tables. CSMA does not have a feature to avoid the problem of one workstation dominating a conversation. In the following screen, we will discuss the 3 types of LAN transmission methods.
Let's now discuss the flavors of LAN transmission methods. There are 3 flavors of LAN transmission methods. They are unicast, the packet is sent from a single source to a single destination address; multicast, the source packet is copied and sent to specific multiple destinations on the network; broadcast, the packet is copied and sent to all the nodes on the network or segment of a network. Let us identify various network devices in the following. Repeaters and hubs operate at the physical layer of the OSI model. Repeaters amplify the data signal to extend the length of a network segment. Hubs and repeaters are used to connect multiple LAN devices, such as servers and workstations. Bridges also amplify data signals. If the destination computer is on the local network segment, it does not forward the data. Bridges operate at the data link layer and OSI layer 2. They do not use IP addresses. IP information is attached in the network layer, layer 3. Bridge automatically forwards any broadcast traffic to all ports. An error state known as a broadcast storm can develop, overwhelming the network devices. A switch is similar to a bridge or a hub. Switches send the data packet only to the specified port where the destination MAC address is located. A switch relies on the MAC address to determine the source and destination of a packet, which is layer 2 networking. Switches primarily operate at the data link layer, layer 2, although intelligent layer 3 switching techniques, combining, switching, and routing, are more frequently used. Although most standard switches operate at the data link layer, layer 3 switches operate at the network layer and function like a router by incorporating some router features. Routers add more intelligence to the process of forwarding packets. When a router receives a packet, it looks at the network layer source and destination addresses, IP address, to determine the path the packet should take, and forwards the packet only to the intended network. This prevents unnecessary network traffic from being sent over the network by blocking broadcast information and traffic to unknown addresses. Routers operate at the network layer, layer 3 of the OSI protocol model. Routers are necessary when communicating between virtual LANs, VLANs. A wireless access point, WAP, is a device that allows wireless devices to connect to a wired network using Wi-Fi, Bluetooth, or related standards. The WAP usually connects to a router via a wired network and can relay data between the wireless devices, such as computers or printers, and wired devices on the network. A hotspot is a common public application of WAPs where wireless clients can connect to the internet without regard for the particular networks to which they have attached for the moment. A collection of connected hotspots can be referred to as a lily-pad network. VLAN is a collection of nodes that are grouped together in a single broadcast domain and a switch and are based on something other than physical segment location. Virtual local area networks, VLANs, allow the ports on the same or different switches to be grouped so that the traffic is confined to the members of that group only. It also restricts broadcast, unicast, and multicast traffic. A VLAN creates an isolated broadcast domain, and a switch with multiple broadcast domains similar to a router. A VLAN also restricts flooding to only those ports included in the VLAN. However, VLANs cannot route from one to another. Such routing would defeat the purpose of the VLAN to isolate the traffic from the general traffic flow. VLANs can aid in isolating segments with sensitive data from the rest of the broadcast domain and can increase security assurance. They can reduce the number of router hops and increase the usable bandwidth. VLANs reduce routing broadcast because ACLs control the stations and the traffic they receive. VLANs are segmented logically rather than physically. They may be created to segregate job or department functions that require heavy bandwidth without affecting the rest of the network. VLANs can span across multiple switches, and you can have more than one VLAN on each switch. For multiple VLANs on multiple switches to be able to communicate via a single link between the switches, you must use a process called trunking. Trunking is a technology that allows information from multiple VLANs to be carried over just one link between switches. The VLAN trunking protocol, VTP, is a protocol that switches use to communicate amongst themselves about VLAN configuration. When a VLAN is implemented with private port or single user switching, it provides fairly stringent security because broadcast vulnerabilities are minimized. A closed VLAN authenticates a user to an access control list on a central authentication server, where the user is assigned authorization parameters to determine his or her level of network access.
Gateways are the software products that can be run on computers or other network devices. They can be multi-protocol and can examine the entire packet. Mail gateways are used to link dissimilar mail programs. Gateways can also be used to translate between two dissimilar network protocols. Microsoft Windows described the standard networking feature as Internet Connection Sharing, which acts as a gateway, offering a connection between the Internet and an internal network. Such a system might also act as a Dynamic Host Configuration Protocol, or DHCP server. DHCP is a protocol used by networked devices or clients to obtain various parameters necessary for the clients to operate in an Internet Protocol IP network. By using this protocol, system administration workload decreases, and devices can be added to the network with minimal or no manual configurations. In the next screen, we will focus on network access control devices.
Network access control devices are used to allow only the legitimate traffic on the network. An example is a firewall. Firewalls were invented in the 1980s. These devices are placed at a network boundary designed to block unwanted incoming or outgoing traffic. A firewall works by examining each packet and consulting a list of rules to determine whether the packet should be permitted to pass through the firewall or be blocked. In a large organization, the list of rules in a firewall can become heavy, possibly resulting in unwanted traffic entering or leaving the network. In the next screen, we will look at the types of firewalls act as perimeter access control devices. Firewalls are categorized into packet filtering, application level, circuit level, and stateful inspection. Packet filtering firewall. The packet filtering firewall examines the source and destination address of the incoming data packet. This firewall either blocks the packet or passes it to its intended destination network. The firewall can allow or deny the access to the specific applications or services based on the access control lists, ACLs. The firewall can be configured to allow access to authorized application port or service numbers only. It looks at the data packet to get information about the source and destination addresses of an incoming packet, the session's communication protocol, such as TCP, UDP, or ICMP, and the source and destination application port for the desired service. A packet-level firewall does not keep a history of the communication sessions. It operates at the network layer of the OSI model and offers good performance. A dynamic packet filtering firewall employs a technology that enables the modification of the firewall security rule. This type of technology is used mostly for providing limited support for UDP. Application-level firewall. An application-level firewall is commonly a host computer that is running proxy server software, making it a proxy server. This firewall works by transferring a copy of each accepted data packet from one network to another, thereby masking the data's origin. A proxy server can control which services a workstation uses on the Internet. It also aids in protecting the network from outsiders who may be trying to get information about the network's design. It inspects the packet up through the application layer and can make access decisions based on the content of the packets. Also called an application layer gateway, the application level firewall is commonly used with a dual-homed host. It operates at the OSI protocol layer 7, the application layer. It is more secure because it examines the packet at the application layer, but it does so at the expense of performance. It controls the services a workstation uses on the Internet, and it aids in protecting the network from outsiders who may be trying to get information about the networks designed. As opposed to packet firewalls, proxy firewalls capture some session history. Proxy firewalls have higher protocols carried on low-level protocols, such as email or HTML. Circuit-level firewall. Similar to an application-level firewall, a circuit-level firewall is used as a proxy server. Although it is similar to the application-level firewall, This firewall does not need a special proxy application software. Circuit-level firewall creates a virtual circuit between the workstation client or destination and the server or host. It works at the session layer of the OSI model and does not carry out deep packet inspection. It also provides security for a wide variety of protocols and is easy to maintain, and takes decisions based upon protocol header and session information. For example, Socket Secure, SOCS, creates a circuit between client and server without requiring knowledge about the internet working service, as is, no application-specific controls.
A stateful inspection firewall intercepts incoming packets at the network layer and then uses an inspection engine to extract state-related information from upper layers. This firewall maintains the information in a dynamic state table and evaluates subsequent connection attempts. Stateful inspection firewalls keep low protocol records at the IP level. The packets are queued and analyzed at all OSI layers against the state table. By examining the state and context of the incoming data packets, protocols that are considered connectionless, such as UDP-based applications and remote procedure calls, RPCs, can be tracked easily. Let us understand the firewall architectures in the following screen.
The four basic types of firewall architectures are packet filtering routers, screened host firewalls, dual-homed host firewalls, and screened subnet firewalls. Some of these architectures are specifically associated with one of the previously discussed firewall types, while other architectures can employ a combination of types. Packet filtering routers. Packet filtering router is the common and oldest firewall device in use. A packet filtering router is located between the private trusted network and the untrusted network or network segment. This firewall architecture is used as a packet filtering firewall. A packet filtering router is sometimes used to directly manage access to a demilitarized zone (DMZ) network segment. A DMZ is a network added between an internal network and an external network to provide an additional layer of security. It is also called a perimeter network. Screened host firewalls. A screened host firewall uses two network cards to connect to the trusted and untrusted networks. However, it adds a screening router between the host and the untrusted network. It provides network layer or routing and application layer or proxy services. This type of firewall system requires an intruder to penetrate two separate systems before he or she can compromise the trusted network. The host is configured between the local trusted network and untrusted network. Since the firewall can be the focus of external attacks, it is sometimes called the sacrificial lamb. Dual-homed host firewalls. A dual-homed host has two network interface cards, NICs, but no screening router. It uses two NICs to attach to two separate networks, commonly a trusted network and an untrusted network. This architecture is a simple configuration that consists of a single computer, the host, with two NICs, one connected to the local trusted network and the other connected to the internet or an untrusted external network. A dual-homed host firewall usually acts to block or filter some or all of the traffic trying to pass between the networks. Screened subnet firewalls. A screened subnet firewall also uses two NICs. It has two screening routers with the host acting as a proxy server on its own network segment. One screening router controls local traffic to the network, while the second monitors and controls incoming and outgoing internet traffic. It employs two packet filtering routers and a bastion host. Let's now take a look at some important network security terms, such as demilitarized zone, DMZ, bastion host, and endpoint security. Demilitarized zone, DMZ. DMZ, also known as perimeter networking, is a physical or logical subnetwork that contains and exposes an organization's external services to a larger untrusted network, usually the internet. It is the buffer zone between an unprotected network and a protected network that allows for the monitoring and regulation of traffic between the two. The purpose of a DMZ is to add a layer of security to an organization's local area network, LAN. The name is derived from the term demilitarized zone, an area between nation-states in which military action is not permitted. Bastion host. A bastion host is any computer that is fully exposed to attack by being on the public side of the demilitarized zone, DMZ, unprotected by a firewall or filtering router. Firewalls and routers, anything that provides perimeter access control security, can be considered bastion hosts. Other types of bastion hosts can include web, mail, DNS, and FTP servers. Endpoint security. It is an information security concept which assumes that each device or endpoint is responsible for its own security. Traditionally, firewalls, central virus scanners, and other intrusion detection or intrusion prevention devices are responsible for securing an endpoint. Endpoint security places the responsibility of security on the device. Some of the examples are broadband users increasing use of desktop firewalls, spam, and antivirus software. It also includes the protection of a business's network from employee memory devices that may unknowingly contain malware. Firewall administrator at Nutri Worldwide Inc. has been working on a new firewall. The firewall is able to do a deep packet inspection on all the layers mentioned in the OSI model. The firewall is transparent to the user and is context-based. It can also discard unsolicited packets arriving in the network from the internet. Which type of firewall is Kevin working on? It is a stateful inspection firewall. Learn about networks in this screen. A data network consists of 2 or more computers connected for the purpose of sharing files, printers, data, and so forth. To communicate on the network, every workstation must have an NIC inserted into the computer, a transmission medium such as copper, fiber, or wireless, a network operating system or NOS, and a LAN device such as a hub, bridge, router, or switch to physically connect the computers together. In addition to these local area networks, there are 2 other common types of LANs: Campus Area Network, or CAN, and Metropolitan Area Network, or MAN. Campus Area Network is a typically large campus network that connects multiple buildings with each other across a high-performance switched backbone on the main campus. Metropolitan Area Network, or MAN, is essentially a LAN that extends over a city or metropolitan area. It is commonly a backbone network that connects business to WANs, often using SONET or FDDI rings provided by the telecommunications vendors. MAN is, however, not often used as a description. Let us look at the types of networks in this screen. Internet is a global network of public networks and Internet service providers, or ISPs, throughout the world. Internet can be utilized either by the public or private network with a VPN. An intranet is an Internet-like logical network that uses a firm's internal physical network infrastructure. Intranet provides more security and control than the public posting on the Internet. Extranet is a private network that uses Internet protocols. In contrast to an intranet, certain users outside the company, such as partners, vendors, etc., can access an extranet. However, the general public will not have the access. A wide area network, or WAN, is a network of subnetworks that are physically or logically interconnected over a larger geographic area than the LANs. A WAN may be privately operated for a specific user community, may support multiple communication protocols, or may provide network connectivity and services via interconnected network segments such as extranets, intranets, and VPNs. WAN technologies will be explained in the following screen. Area network, or WAN, is a network of subnetworks that are physically or logically interconnected over a larger geographic area than LANs. Local area networks, LANs, and metro area networks, MANs, are combined to form WANs. A WAN may be privately operated for a specific user community, may support multiple communication protocols, or may provide network connectivity and services via interconnected network segments such as extranets, intranets, and VPNs. To become familiar with the various types of WAN technologies, you must understand WAN protocols, topologies, and devices. Similar to LAN protocols, WAN protocols are the rules for communicating between computers on a WAN. Since WAN is often used for connecting diverse networks, these protocols address the issues involved with communications between many large and unrelated networks. WANs use packet switching and circuit switching technologies. The different types of WAN technologies are WAN switching and devices, network address translation, NAT, frame relay, multi-protocol label switching, MPLS, and voice over internet protocol, VoIP. WAN switching is required when the network grows and needs more than a single point-to-point connection. There are 2 main flavors of WAN switching: circuit switching and packet switching. Circuit switch networks. Circuit switching is defined as a switching system in which a dedicated physical circuit path must exist between the sender and receiver for the duration of the transmission or the call. A circuit switch network describes a type of WAN that consists of a physical, permanent connection from one point to another. This technology is older than packet switching. Telephone is an example of circuit switch networks. Packet switch networks. Packet switching is defined as a networking method where nodes share bandwidth with each other by sending small data units called packets. A packet switch network, PSN or PSDN, is a network that uses packet switching technology for data transfer. In contrast to circuit switch networks, the data in packet switch networks is broken into packets and then sent to the next destination based on the router's understanding of the best available route. Examples of packet switch networks include frame relay and VoIP. Common WAN devices. WAN devices enable the use of WAN protocols in topologies. The following are examples of these device types. Routers. Routers are extremely important in the WAN environment, especially for IP internet traffic. Multiplexers. Commonly referred to as a MUX, a multiplexer is a device that enables more than one signal to be sent out simultaneously over one physical circuit. WAN switches. WAN switches are multi-port networking devices that are used in carrier networks. They operate at the data link layer and typically switch frame relay and X.25. These switches connect private data over public data circuits by using digital signal. Address translation, or NAT, describes the process of converting an IP address valid within one network to a different IP address valid within another network. In other words, NAT converts a private IP address on the inside, trusted network to a registered real IP address seen by the untrusted outside network. The Internet Assigned Number Authority, IANA, has reserved 3 blocks of the IP address space for private Internet addresses: 10.0.0.0 through 10.255.255.255, 172.16.0.0 through 172.31.255.255, 192.168.0.0 through 192.168.255.255. Frame relay is a high-performance WAN protocol that operates at the data link layer of the OSI model. Originally designed for use across ISDN interfaces, it is currently used with a variety of other interfaces and is a major standard for high-speed WAN communications. Frame relay is a successor to X.25 and LAPB. It is the fastest of the WAN protocols listed because of its simplified framing approach, which utilizes no error correction. Frame relay uses SVCs, PVCs, and data link connection identifiers, DLCIs, for addressing. Since it requires access to a high-quality digital network infrastructure, it is not available as a mechanism that directs data from one network node to the next based on short path labels. The labels identify virtual links or paths between distant nodes rather than endpoints. MPLS can encapsulate packets of various network protocols. It can be used to carry different kinds of traffic, including both voice telephone traffic and IP packets. MPLS operates at a layer 2.5. Voice over Internet Protocol is a category of hardware and software. It enables people to use the Internet as the transmission medium for telephone calls by sending voice data in packets using IP rather than by traditional circuit transmissions of the PSTN. VoIP is one of the several digital multi-service access IP technologies that combine many types of data, such as voice, audio, and video into a single IP packet, which provides major benefits in the areas of cost, interoperability, and performance.
Fiber Channel over Ethernet, or FCOE, is a computer network technology that enables fiber channel communications to run directly over Ethernet. It allows fiber channel to use 10 gigabit Ethernet networks or higher speeds while preserving the fiber channel protocol. FCOE converges storage and IP protocols on a single cable transport and interface by moving fiber channel traffic across existing high-speed Ethernet infrastructure. Internet Small Computer System Interface, or ISCSI, is a transport layer protocol that defines how small computer system interface, or SCSI packets, should be transported over a TCP/IP network. ISCSI enables data transfers over intranets and manages storage over long distances. It can be used to transmit data over local area networks or LANs, wide area networks or WANs, or the Internet. It can also enable location-independent data storage and retrieval. Let us discuss virtualized networks in the following slide. Virtual Storage Area Network, or vSAN, is a collection of ports from a set of connected fiber channel switches that forms a virtual fabric. Ports within a single switch can be partitioned into multiple vSANs, despite sharing hardware resources. vSAN allows isolation of traffic within particular portions of a storage area network or SAN by creating a logical partition. Software-defined networking, or SDN, allows network administrators to support a network fabric across multi-vendor equipment by decoupling the control from the physical infrastructure. Some of the limitations of SDN are complexity, inability to scale, and vendor dependence. Guest operating systems in a virtual machine is the operating system or OS that is installed in addition to the host or main OS. Security practitioners must ensure that the host system is hardened. In the next screen, we will focus on remote access.
Let's now learn about remote access. Remote access technologies can be defined as the data networking technologies that are uniquely focused on providing the remote user, such as telecommuter, internet or intranet user, or extranet user or partner, the access into a network, while striving to maintain the principal tenets of confidentiality, availability, and integrity. There are many advantages of employing secure remote network access. Remote access technologies reduce networking costs by using the internet to replace expensive dedicated network lines. They provide employees with flexible work styles, such as telecommuting. They build efficient ties with customers, suppliers, and employees. Let us look at remote access protocols in the following screen. Remote access protocols include VPN using PPTP and L2TP, Internet Protocol Security, IPSec, Secure Socket Layer, SSL, Secure HTTP, SHTTP, and Secure Shell, SSH. VPN is created by building a secure communication link between two nodes, emulating the properties of a point-to-point private link. A VPN can be used to facilitate remote access, VPN, network-to-network VPN, and intranet access VPN. VPN and remote access protocols are point-to-point tunneling protocol, PPTP, and Layer 2 tunneling protocol, L2TP. PPTP works at the data link layer of the OSI model. It is designed for individual client-to-server connections, hence, it allows only a single point-to-point connection per session. PPTP allows IP, IPX, or NetBEUI traffic to be encrypted and then encapsulated in an IP header. This IP header will be sent across a corporate IP internetwork or a public IP internetwork, such as the Internet. L2TP is a combination of PPTP and Layer 2 forwarding protocol, L2F, and also works at the data link layer. Similar to PPTP, L2TP was designed for a single point-to-point client-to-server connections. L2TP allows IP, IPX, or NetBEUI traffic to be encrypted and then sent over any medium that supports point-to-point datagram delivery, such as IP, X.25, frame relay, ATM,
Let us
etc.
look at
Internet Protocol Security, or IPSec, in this screen. Internet Protocol Security, IPSec, is a protocol suite for securing Internet Protocol, IP communications, by authenticating and encrypting each IP packet of a communication session. IPSec also includes protocols for establishing mutual authentication between agents at the beginning of the session and negotiation of cryptographic keys to be used during the session. IPSec, Internet Protocol Security suite of protocols adds a cryptographic layer to both IP version 4 and IP version 6. It is one of the methods for providing virtual private networks, VPN, which allow you to send private data over an insecure network such as the Internet. The data crosses a public network but is virtually private. The two basic security protocols, Authentication Header, AH, and Authentication Protocol and Encapsulating Security Payload, ESP, and Authentication and Encryption Protocol. In the next screen, we will look at the modes of operation on IPSec. Two modes of IPSec operation are as follows. In tunnel mode, IPSec is used to protect a complete encapsulated IP datagram after the IP header has already been applied to it. The IPsec headers appear in front of the original IP header, and then a new IP header is added in front of the IPsec header. That is to say, the entire original IP datagram is secured and then encapsulated within another IP datagram. Tunnel mode used by security gateways, which can provide point-to-point IPsec tunnels. It encrypts the entire packet. The payload and header are protected, that is, encryption and hash, used for network-to-network, host-to-network, and host-to-host communications. As its name suggests, in transport mode, the protocol protects the message passed down to IP from the transport layer. The message is processed by ESP and the appropriate headers added in front of the transport UDP or TCP header. The IP header is then added in front of that by IP. Another way of looking at this is as follows. Normally, the transport layer packages data for transmission and sends it to IP. From IP's perspective, this transport layer message is the payload of the IP datagram. When IPsec is used in transport mode, the IPsec header is applied only over this IP payload, not the IP header. So in this mode, only the payload is protected, that is, encryption and hash. IP headers are not encrypted. If AH is used, then IP address cannot be translated, that is, NAT. It is used for host-to-host communications only. In the next screen, we will understand IPsec security protocol. Authentication header, AH, provides authentication and integrity for each packet of network data. It offers no confidentiality, but rather acts as a digital signature for the data. AH also protects against replay attacks, where data is sniffed off a network and resent, often in an attempt to fraudulently reuse encrypted authentication credentials. AH operates directly on top of IP using IP protocol number 51. In AH transport mode, the IP packet is modified only slightly to include the new AH header between the IP header and the protocol payload, TCP, UDP, etc., and there is a shuffling of the protocol code that links the various headers together. This protocol shuffling is required to allow the original IP packet to be reconstituted at the other end. After the IPsec headers have been validated upon receipt, they're stripped off, and the original protocol type, TCP, UDP, etc., is stored back in the IP header. It provides data authentication only, no encryption. It is implemented on the communicating endpoints, useful when encryption is not needed or is not permitted. Tunnel mode creates a new IP header and uses it as the outermost IP header of the datagram. The AH header follows the new IP header. The original datagram, both the IP header and the original payload, comes last. AH authenticates the entire datagram, which means that the responding system can detect whether the datagram changed while in transit. When either ends of a security association is a gateway, use tunnel mode. In tunnel mode, the source and destination addresses in the outermost IP header do not need to be the same as those in the original IP header. For example, two security gateways may operate an AH tunnel to authenticate all traffic between the networks they connect together. In fact, this is a very typical configuration. The main advantage to using tunnel mode is that tunnel mode totally protects the encapsulated IP datagram. In addition, tunnel mode makes it possible to use private addresses. Transport mode encapsulates just the datagram's payload and is designed strictly for host-to-host communications. The original IP header is left in place except for the shuffled protocol field, and it means that, among other things, the source and destination IP addresses are unchanged. It provides confidentiality for the segment's payload, data authentication for the packet's headers and payload, or both. It is implemented on the communicating endpoint. Encapsulating security payload, ESP, is a member of the IPsec protocol suite. In IPsec, it provides origin authenticity, integrity, and confidentiality protection of packets. ESP also supports encryption-only and authentication-only configurations, but using encryption without authentication is strongly discouraged because it is insecure. Unlike authentication header, AH, ESP in transport mode does not provide integrity and authentication for the entire IP packet. However, in tunnel mode, where the entire original IP packet is encapsulated with the new packet header added, ESP protection is afforded to the whole inner IP packet, including the inner header, while the outer header, including any outer IPv4 options or IPv6 extension headers, remain unprotected. ESP operates directly on top of IP, using IP protocol number 50. ESP in tunnel mode encapsulates an entire IP datagram inside the encrypted shell. It provides confidentiality, authentication, or both for entire original packet. It must be implemented on IPsec gateways, acting as such. An additional IP header identifying the gateways is prepended. The next slide deals with the components of the IPsec process. IP security architecture uses the concept of a security association as the basis for building security functions into IP. A security association is simply the bundle of algorithms and parameters, such as keys, that is being used to encrypt and authenticate a particular flow in one direction. Therefore, in normal bidirectional traffic, the flows are secured by a pair of security associations. Authentication header, or AH, and encapsulating security payload, or ESP, may be used separately or in combination. An IPsec security association, or SA, is a simplex one-way connection that may be used to negotiate ESP or AH parameters. If two systems communicate via ESP, they use two SAs, one for each direction. If the systems leverage AH in addition to ESP, they use two more SAs, for a total of 4. Each simplex SA connection is identified by a unique 32-bit number known as the Security Parameter Index, or SPI. The SA process is managed by Internet Security Association and Key Management Protocol, or ISA-KMP. It provides a key exchange framework, negotiates establishment, modification, and deletion of SAs. It also negotiates key exchange protocol to be used. The Internet Key Exchange, or IKE protocol, is a key management protocol standard that is used in conjunction with the IPsec standard. IKE enhances IPsec by providing additional features, flexibility, and ease of configuration for the IPsec standard. IPsec can, however, be configured without IKE. A variety of encryption algorithms like AES, DES, MD%, SHA-1 can be employed by IPsec. Internet Key Exchange, IKE, negotiates the algorithm selection process. Benefits provided by IKE include the following: eliminates the need to manually specify all the IPsec security parameters in the crypto maps at both peers, allows specifying a lifetime for the IPsec security association, allows encryption keys to change during IPsec sessions, allows IPsec to provide anti-replay services, permits certification authority CA support for a manageable, scalable IPsec implementation, allows dynamic authentication of peers. Let us look at a flowchart of IPsec process in the next slide. IPsec involves many component technologies and encryption methods, yet IPsec's operation can be broken down into 5 main steps. Interesting traffic initiates the IPsec process. Traffic is deemed interesting when the IPsec security policy configured in the IPsec peers starts the IKE process. IKE Phase 1. IKE authenticates IPsec peers and negotiates IKE SAs during this phase, setting up a secure channel for negotiating IPsec SAs in Phase 2. IKE Phase 2. IKE negotiates IPsec SA parameters and sets up matching IPsec SAs in the peers. Data is transferred between IPsec peers based on the IPsec parameters and keys stored in the SA database. IPsec tunnel termination. IPsec SAs terminate through deletion or by timing out. Some common security protocols in this screen. Pretty Good Privacy, PGP, was designed by Phil Zimmerman as a freeware email security program and was released in 1991. It was the first widespread public key encryption program. PGP is a complete crypto system that uses cryptographic protection to protect email and files. It can use RSA public key encryption for key management and use IDEA symmetric cipher for bulk encryption of data, although the user has the option of picking different types of algorithms for these functions. PGP can provide confidentiality by using the IDEA encryption algorithm, integrity by using the MD5 hashing algorithm, authentication by using the public key certificates, and non-repudiation by using cryptographically signed messages. PGP uses its own type of digital certificates rather than what is used in PKI, but they both have similar purposes. The user's private key is generated and encrypted when the application asks the user to randomly type on her keyboard for a specific amount of time. Instead of using passwords, PGP uses passphrases. The passphrase is used to encrypt the user's private key that is stored on her hard drive. PGP does not use a hierarchy of CAs or any type of formal trust certificates, but instead relies on a web of trust in its key management approach. Each user generates and distributes his or her public key, and users sign each other's public keys, which creates a community of users who trust each other. This is different from the CA approach, where no one trusts each other. The only trust is the CA. The signer must be regarded as a trusted introducer. A collection of signed keys is referred to as a key ring. Though their names are very similar, there is a difference between secure HTTP, SHTTP, and HTTP Secure, HTTPS. SHTTP is a technology that protects each message sent between two computers, while HTTPS protects the communication channel between two computers, messages and all. HTTPS uses SSL, TLS, and HTTP to provide a protected circuit between a client and server. So, SHTTP is used if an individual message needs to be encrypted, but if all information that passes between two computers must be encrypted, then HTTPS is used, which is SSL over HTTP. Unlike HTTP, it is a stateful protocol. The initial connection remains up between exchanges. An SHTTP session is identified by URLs with SHTTP:// HTTP Secure, HTTPS, is HTTP running over SSL. HTTP works at the application layer, and SSL works at the transport layer. Secure Sockets Layer, SSL, uses public key encryption and provides data encryption, server authentication, message integrity, and optional client authentication. When a client accesses a website, that website may have both secured and public portions. The secured portion will require the user to be authenticated in some fashion. When the client goes from a public page on the website to a secured page, the web server will start the necessary tasks to invoke SSL and protect this type of communication. HTTPS uses standard port 443. It encrypts all information that passes over the connection at the session layer. Unlike SHTTP, SSL can be applied to non-HTTP traffic. An HTTPS session is identified by URLs with HTTPS://. The SSL protocol was developed by Netscape in 1994 to secure Internet client-server transactions. Mostly used for e-commerce applications, the SSL protocol authenticates the server to the client using public key cryptography and digital certificates. In addition, this protocol provides for optional client-to-server authentication. It supports the use of RSA public key algorithms, IDEA, DES, and 3DES private key algorithms, and the MD5 hash function. The general steps are as follows. The client, that is the browser, requests a server. The server sends its digital certificate to the client. The CA verifies the server's public key, and the client generates a symmetric key session. The session key is encrypted with the server's public key and sent to the server. Server and browser can now send encrypted messages. An SSL session is identified by URLs starting with HTTPS://. Secure Electronic Transaction, SET, is a security technology proposed by Visa and MasterCard to allow for more secure credit card transaction possibilities than what is currently available. SET has been waiting in the wings for full implementation and acceptance as a standard for quite some time. Although SET provides an effective way of transmitting credit card information, businesses and users do not see it as efficient because it requires more parties to coordinate their efforts, more software installation and configuration for each entity involved, and more effort and cost than the widely used SSL method. SCT is a cryptographic protocol and infrastructure developed to send encrypted credit card numbers over the Internet. The following entities would be involved with an SCT transaction, which would require each of them to upgrade their software and possibly their hardware: electronic wallet, digital certificate holding user financial information, software running on the merchant's web server, and payment server at the merchant. Let's now discuss the various types of remote access security methods. Restricted address. This method filters out unauthorized users based on their source protocol address, IP, or other LAN protocol. Caller ID. It checks the incoming phone number of the caller against an approved phone list before accepting the session. Callback. A user attempting to initiate the session supplies a password or some type of identifying code. The access server then hangs up and calls the user back at a predetermined phone number. Let's now discuss various types of multimedia collaborations. Remote or virtual meetings. These are real-time interactions that take place over the Internet using integrated audio and video, chat tools, and application sharing. Instant messaging, abbreviated as IM, is a type of communication service that enables you to create a private chat room with another individual to communicate real-time over the Internet. Telecollaboration refers to a set of software technologies that enable the integration and extension of personal desktop collaboration into high-definition video conferencing solutions. Telepresence, a set of technologies which allows a person to feel as if they were present, to give the appearance of being present, or to have an effect via telerobotics at a place other than their true location. The next screen will focus on wireless technology. Technology is the fastest growing area of network connectivity. Security is an extreme concern here because all wireless technologies, mobile phones, satellite transmissions, and so forth, are inherently susceptible to interception. Encryption standards are rapidly being developed to combat this problem. There are various wireless technologies, such as IEEE wireless standards, spread spectrum technologies, direct sequence spread spectrum, and frequency hopping spread spectrum. IEEE 802.11 refers to a family of specifications for WLANs developed by a working group of the IEEE. 802.11 also generically refer to the IEEE committee responsible for setting the various wireless LAN standards. The 802.11 specification identifies an over-the-air interface between a mobile device wireless client and a base station, or between two mobile device wireless clients. The original IEEE wireless LAN standard that provides 1 or 2 Mbps transmission speed in the 2.4 GHz band using either FHSS or DSSS, which is covered later in the spread spectrum technologies. The modulation used in 802.11 is commonly phase shift keying, PSK. Spread spectrum uses a radio transmission mode that broadcasts signals over a range of frequencies. The receiving mobile device must know the correct frequency of the spread spectrum signal being broadcast. Two different spread spectrum technologies for 2.4 GHz wireless LANs currently exist: direct sequence spread spectrum, DSSS, and frequency hopping spread spectrum, FHSS, is a wideband spread spectrum transmission technology that generates a redundant bit pattern for each bit to be transmitted. DSSS spreads the signal over a wide frequency band, in which the source transmitter maps each bit of data into a pattern of chips. The DSSS transmitter and receiver must be synchronized to operate properly. DSSS spreads across the spectrum, but the number of independent, non-overlapping channels in the 2.4 GHz band is small, typically only 3. Some DSSS products enable users to deploy more than one channel in the same area by separating the 2.4 GHz band into multiple subbands, each of which contains an independent DSSS network. FHSS uses a narrow-band carrier that continually changes frequency in a known pattern. The FHSS algorithm spreads the signal by operating on one frequency for a short duration and then hopping to another frequency. The minimum number of frequencies engaged in the hopping pattern and the maximum frequency dwell time, how long it stays on each frequency before it changes, are restricted by the FCC, which requires that 75 or more frequencies be used with the maximum dwell time of 400 milliseconds. IEEE 802.11 wireless networks operate in one of two operational modes: ad hoc mode and infrastructure mode. Ad hoc mode. In ad hoc mode, each mobile device client communicates directly with the other mobile device clients within the network. Ad hoc mode is designed so that only the clients within transmission range, within the same cell, of each other can communicate. Infrastructure mode. Each mobile device client in infrastructure mode sends all of its communications to a network device called an access point, AP. The access point acts as a bridge does in LAN and forwards the communications to the appropriate network, either the WLAN or another wireless network. The wireless standard of 802.11 family are 802.11a, specified speeds up to 54 Mbps in the 5 GHz band, 802.11b, specified speeds of up to 11 Mbps in the 2.4 GHz band, 802.11g, specified speeds of up to 54 Mbps in the 2.4 GHz band, 802.11n, specified speeds of up to 130 Mbps in the 2.4 GHz or 5 GHz band, and 802.11i, specified speeds of security protocol. In the next screen, we will learn about Bluetooth as a wireless personal area network, PAN, technology for relatively low-speed data communication over short distances. It is a peer-to-peer protocol created to connect multiple consumer mobile information devices transparently, such as cellular phones, laptops, handheld computers, digital cameras, printers, etc. Bluetooth uses the IEEE 802.15 specification in the 2.4 to 2.5 GHz band with FHSS technology. Bluetooth enables mobile devices to avoid interference from other signals by hopping to a new frequency after transmitting or receiving a packet. Typical Bluetooth applications include wireless mobile phone headsets, computer mice and keyboards, wireless stereo headphones, and GPS receivers. Since Bluetooth uses radio spectrum, devices do not require line of sight to connect. Bluetooth data rates range from 1 megabit per second to 3 megabits per second. Bluetooth's power consumption is very low, which makes it suitable for low-power devices. The maximum range for communications is 10 meters. Bluetooth devices can authenticate through a process called pairing, during which two devices can exchange a cryptographic secret key that the two devices can later use to securely identify themselves. Communications between paired devices can also be encrypted. Bluetooth operates in two modes, discovery mode and automatic types of attacks that can be carried out on a Bluetooth-enabled device are explained in this screen. They are bluejacking, blue snarfing, blue bugging, backdoor attacks, and denial of service attacks. When you pair the Bluetooth devices, a message will normally appear on your handset. The message can be up to 248 characters in length and is often abused by others as a method of sending messages to your device. Your device will display the message and then ask you for permission to pair your device with the attacker. This can be a precursor to other attacks, especially if the message tells you that you have won something and goes on to say that you need to input a specific 4-digit code to collect your prize. If you were to type in this 4-digit code, the pairing passcode, your device would then be open for any of the other attacks. The term snarf refers to taking a large document or file for the purpose of using it with or without the author's expressed permission. On many Bluetooth devices, it is possible to complete the pairing process without informing the user of the target handheld. Once the connection is established, the attacker can gain access to restricted information. This information can be anything from pictures, files, contracts, device settings, calendar information, as well as serial and SIM numbers that uniquely identify your phone. This type of vulnerability can allow an attacker to create a serial connection to the target device. The attacker could then initiate calls, sometimes to international or pay-per-minute numbers, forward calls, send and receive SMS messages, connect to the internet, and even monitor calls on a GSM phone. Attacks of this nature can often provide the attacker with the tools he or she will need to steal your identity and possibly cause damage to the user financially. Every Bluetooth user knows about pairing, which is the action of linking two Bluetooth-capable devices for the purpose of transferring data. Backdoor attacks. This attack is carried out through the specific pairing mechanism by establishing a trust relationship between the user's device and the attacker's laptop or PDA. DOS attacks. These type of attacks serve only to be annoyance to the target user's device. The attacker can use his or her Bluetooth device to send many pairing requests to the user's Bluetooth handset. It can, however, temporarily paralyze a phone or PDA and cause a notable drain on the battery as well. Let's now learn about various wireless security systems. Wireless is one of the newest communication technology frontiers, offering the possibility of always-on, instant mobile communications. Uses airways for communication makes it more vulnerable for attacks. With the abundant use of wireless-enabled devices like laptops, etc., it is difficult to secure, manage, and roll out. However, the vulnerabilities inherent to wireless computing present daunting hurdles. Some of the wireless vulnerabilities are DOS attacks. A denial of service, DOS attack, is an example of the failure of the tenet of availability. WAP gap. A specific security issue that is associated with WAP is the WAP gap. A WAP gap results from the requirement to change security protocols at the carrier's WAP gateway from the wireless WTLS to SSL for use over the wired network. Insertion attacks. In an insertion attack, unauthorized devices are deployed to gain access to an existing network. Rogue access point. An insertion attack could be facilitated by the deployment of rogue access points, either by a hacker or by well-meaning internal employees seeking to enhance wireless coverage. WEP weakness. Most WEP products implement a 64-bit shared key, using 40 bits of this for the secret key and 24 bits for the initialization vector. The key is installed at the wired network AP and must be entered into each client as well. Service Set Identifier, SSID issue. The Service Set Identifier, SSID, is an identification value programmed in the access point or group of access points to identify the local wireless subnet. This segmentation of the wireless network into multiple networks is a form of authentication check. Wireless scanning and eavesdropping. Wireless technology is also vulnerable to eavesdropping, especially because intruders do not have to physically tap into a network. War driving. War driving, also war walking, is a term used to describe a hacker who, armed with a laptop and a wireless adapter card, and traveling via a car, bus, subway train, or other form of transport, goes around sniffing for WLANs. Common war driving exploits find many wireless networks with WEP disabled and using only the SSID for access control. Wireless packet sniffers. Wireless packet analyzers, or sniffers, work the same way as wired network packet analyzers. They capture packets from the data stream and allow the user to open them up and look at or decode them. Wireless encryption protocol. There are many different types of wireless encryption protocols. WEP, short for Wired Equivalency Privacy, a security protocol for wireless local area networks, WLANs, defined in the 802.11b standard. LAN. LANs are inherently more secure than WLANs because LANs are somewhat protected by the physicalities of their structure, having some or all part of the network inside a building that can be protected from unauthorized access. WLANs, which are over radio waves, do not have the same physical structure and therefore are more vulnerable to tampering. Wired Equivalency Privacy, WEP, uses stream cipher RC4 for confidentiality and CRC32 checksum for data integrity. WPA PSK is an authentication mechanism in which users provide some form of credentials to verify that they should be allowed access to a network. This requires a single password entered into each WLAN node, access points, wireless routers, client adapters, bridges. As long as the passwords match, a client will be granted access to a WLAN. WPA PSK, pre-shared key mode, is designed for home and small office networks and doesn't require an authentication server. Each wireless network device authenticates with the access point using the same 256-bit key generated from a password or passphrase. WPA and WPA2 Enterprise, also referred to as WPA 802.1x mode and sometimes just WPA, as opposed to WPA PSK. It is designed for enterprise networks and requires a radius authentication server. This requires a more complicated setup, but provides additional security, that is, protection against dictionary attacks on short passwords. 802.1x. The IEEE drafted the 802.1x port-based network access control standard in 2001 to provide enhanced security for users of 802.11b wireless LANs. It provides port-level authentication for any wired or wireless Ethernet client system. 802.11i. IEEE 802.11i 2004 or 802.11i, implemented as WPA2, is an amendment to the original IEEE 802.11. This standard specifies security mechanisms for wireless networks, wireless best practices, change the access point's default SSID, disable the broadcast SSID function on the AP, enable WPA2 for better security, employ MAC address filtering, implement a radius or Kerberos server to provide strong authentication, physically locate the AP in an area that limits its radio emanations, logically put the AP in a DMZ with the firewall between the DMZ and the internal network, implement VPN tunnels, disable DHCP and assign static IP addresses, penetration test regularly, research migrating to 802.11i technologies, change the access point's default admin password to improve the security of the communication channels. Hilda Jacobs was asked to provide suggestions for securing communication. Kevin worked with Hilda in this assignment, and they produced their report. The report suggested that all the site-to-site communication over the public network or internet should use IPSEC. Administrators will have to use SSH instead of Telnet for administration of network devices or servers over the network. SSH provides more secure communication channel as compared to Telnet. Kevin made notes on the disadvantages of Telnet and added it to his CISSP learning material. What is the major disadvantage of using Telnet? Telnet communication is unencrypted, and attacker can easily sniff the data, including passwords. Let's now discuss network attacks. Following are the various ways a network can be attacked. DOS/DDoS. A denial of service DOS attack is an attempt on the part of the attacker to incapacitate a target system or resource. The attack can take one of the two forms, such as high volume and malfunction. High volume attack may consist of a high volume of traffic that is designed to incapacitate the target by causing its resources to become exhausted. Malfunction attack may consist of one or more specially crafted messages that are designed to disable the target by causing its malfunction. Teardrop. A teardrop attack is one in which the attacker sends mangled packet fragments with overlapping and oversized payloads to a target system. Earlier versions of operating systems had bugs in the fragment reassembly code in their TCP/IP drivers that would cause the system to crash. Ping of death. The ping of death, POD, is an attack on a system where the attacker sends a ping packet of length 65,535 bytes to the target system. The TCP/IP protocol will fragment this packet as it travels through the network. It is then reassembled on the target system, causing a buffer overflow. SYN flood. A SYN flood attack is a denial of service attack in which the attacker sends a large number of SYN packets to the target system. A SYN packet is the first packet in a TCP connection three-way handshake. By sending a SYN packet to a system, it allocates resources in memory. Sequence number. A sequence number attack consists of an attacker who attempts to hijack or disrupt an existing TCP session by injecting packets that pretend to originate from one of the two computers in the session. Smurf. A Smurf attack consists of a large number of forged ICMP echo requests. The packets are sent to a target network's broadcast address, which causes all systems on the network to respond. DNS poisoning. DNS poisoning, or DNS spoofing, or DNS cache poisoning, is a computer hacking attack where the data is introduced into a domain name system DNS name server's cache database, thus rerouting a request for a web page and causing the name server to return an incorrect IP address and diverting traffic to another computer, often the attacker's. Rootkit. A rootkit is a tool or collection of tools that an attacker can install on a compromised computer. A rootkit is a stealthy type of malicious software or malware designed to hide the existence of certain processes or programs from normal methods of detection and enable continued privileges access to a computer. Worm. A worm is a type of malware that has the means for automatic self-replication. They spread by exploiting known vulnerabilities that permit the malicious program to infect new victims. Spam. Spam is a common term for unsolicited commercial email, UCE. Spam greatly adds to the volume of email traffic on the internet. Often, the volume of spam is so high that over 90% of all email on the internet is spam. Phishing. Phishing is a type of spam where the content of a message is designed to masquerade a trustworthy organization. The intention is to defraud the recipient by persuading them to an authentic-looking website where they will enter secret information such as user IDs, passwords, bank account or credit card numbers, date of birth, social insurance numbers, and so on. Farming. Farming is a hacker's attack intended to redirect a website's traffic to another, bogus site. Farming can be conducted either by changing the host file on a victim's computer or by exploitation of a vulnerability in DNS server software. IP spoofing attacks. IP address spoofing, or IP spoofing, refers to the creation of Internet Protocol IP packets with a forged source IP address. The purpose is to conceal the identity of the sender or impersonating another computing system. ARP poisoning. ARP spoofing is a computer hacking technique whereby an attacker sends fake, spoofed address resolution protocol, ARP messages, onto a local area network, compromising the victim's ARP tables. Masquerading. Masquerading is the term used when one user pretends to be another user. An attacker socially engineering passwords from an ISP could be an example of masquerading. Let us look at the countermeasures of network attacks in the following access control list. The earliest and the common technique used to block unwanted traffic is the use of access control lists, ACLs, on network routers. ACLs, while they may lack the strength to handle some of the more complex types of TCP/IP sessions that include the use of dynamically allocated ports, they often represent a good first line of defense to block several types of unwanted traffic. Firewalls. Firewalls are devices placed at a network boundary that are designed to block unwanted incoming or outgoing traffic. A firewall works by examining each packet and consulting a list of rules to determine whether the packet should be permitted to pass through the firewall or be blocked. There have been 3 generations of firewalls, which are packet filters, stateful packet filters, and application layer filters. Intrusion Detection System, IDS. Intrusion Detection Systems, IDS, are programs or devices that are designed to observe network communications and generate alerts if any harmful or malicious traffic is detected. There are 2 primary types of IDS, which are network-based IDS, NIDS, and host-based IDS, HIDS. Intrusion Prevention System, IPS. An intrusion prevention system, IPS, is a device or program that not only senses unwanted traffic, but also blocks that unwanted traffic. There are 2 primary types of IPS, which are network-based IPS, NIPS, and host-based IPS, HIPS. Antivirus software. Antivirus software that is installed on servers can detect worms and other malware and prevent them from installing. Private addressing. While the primary purpose of private addressing was to conserve publicly routable IP addresses, a desirable side effect is the fact that systems with private IP addresses are a lot more difficult to attack. Close unnecessary ports and services. A highly effective method to reduce the probability of successful attack is to close all unnecessary and unused ports and services on systems and devices. Security patches. All applicable security patches should be installed on servers and network devices as soon as it is practical to do so. Unified Threat Management, UTM. Unified Threat Management, UTM, is a term used to describe security devices and appliances that perform many functions in order to simplify the defenses in a network. Gateways. A gateway is a general term to join a system or device that provides some intermediary or translating function in a network. Routers, firewalls, and email servers are some of the examples of gateways. In terms of security countermeasures, a gateway is a system or device that provides some protection against one or more threats.
Here's a quick recap of what we have learned in this domain. The communications and network security domain involves developing a secure network architecture and design, securing network components, and communication channels. Security can be addressed more efficiently using the layered approach. The network communication models, such as OSI model, provide a conceptual framework for communication between computers. The use of proper countermeasures provides confidentiality, integrity, availability, and authentication for transmissions over private and public communication networks. This concludes communications and network security. The next domain is identity and access management.